Thank you very much, Seliki, for the introduction, and thanks everyone for being here. And also a special thanks to the organizers for giving me the opportunity to give this talk. So getting right to the topic, the current state of pulsar timing array searches for gravitational wave background. I'm going to talk about this topic first from the perspective of just giving you some background, then showing some work that we did recently in the European pulsar timing array, and conclude with the current state of this research in general. So to begin with, very quickly, a recap of the European Pulsar Timing Array, or EPTA. So the EPTA is a large collaboration in Europe consisting of European institutions and observatories with the aim of using pulsar timing observations for the detection of gravitational waves. This effort, the backbone of this effort, of course, is our 5 large radio telescopes in Europe that you see here pictures that all operate in single telescope mode, but they also work together in a tight array mode for an equivalent telescope of 195 meter radius. So we have been working for many decades on this project, so all the work here deserves credit to a lot of people. And the EPTA obviously has been working alongside the PPTA and Nanograph in Australia and in North America. And with these colleagues, we also have the International Pulsar Timing Array, where we do combine efforts, combining data and analysis since 2010. And there's, of course, a new collaborations emerged in India, China, and South Africa, which are slowly all integrating into the IPTA scene. So getting into the scientific part of the topic, pulsar timing and pulsar timing models. Of course, you all know what a pulsar is, a highly magnetized neutron star that rotates, as we see here in the animation. And what we do is that we observe in time domain these pulses that are seen in our telescopes every time this beamed emission that comes out from the magnetic poles crosses our line of sight. So if we observe this over a long time scale, we get a time series, and we use a timing model to be able to predict the future times of arrival of the pulsars, which we call the TOAs. And obviously, this model contains information on the pulsar rotation, the pulsar orbit if it's in a binary, which could be a relativistic binary, and the pulsar astrometry, but also we need to account for the signal propagation within the interstellar, the ionized interstellar medium, as the signal is broadband and gets dispersed, and so the signal will arrive differently at different frequencies. And we are very interested in the dispersion measure, which is the integrated electron content along the line of sight to the pulsar, of course. And among other things, obviously, we need to take care of using a good reference time standard. We use the best atomic time scales available to us by the BIPM. Since we are observing at different locations, and all the local arrival times are then referred to this time standard. Also, we need to refer all the local arrival times to an inertial reference frame. So we use a solar system barycenter to approximate that. So we use a solar system ephemeris to calculate the position of the solar system barycenter at each observing epoch. And of course, our model needs to account for any stochastic noise in the data. Now, the difference between what we observe and what the model predicts is called the timing residuals, and these residuals allow us to, of course, improve the model and to find any kind of unmodeled signals that could be of interest. Now, the millisecond pulsars in particular are the fastest pulsars that we know of, and they also have the most stable rotations. The TOA measurements of MSPs nowadays can be done with precision of even 50 to a few hundred nanoseconds, which means that we can measure the period of the pulsars with a precision that is about or less than 10 to the minus 17 seconds, which makes MSPs extremely accurate cosmic clock. And we can use them for a wealth of applications, amongst them to probe small changes in light propagation times due to space-time deformations by gravitational waves. And let's see how this works. You see here the pulsar emitting the pulses that we observe with the radio telescope, and we see the space-time deformation due to a passing gravitational wave will either redshift or blue shift the period of the pulsar, which we will observe as time advances or delays in the times of arrival of the pulsar. Now, if we use a pulsar timing array, which is nothing else but an array of pulsars at different sky locations, we should be able to observe this phenomenon in all pulsars in a way that is predicted by theory to verify that this is a gravitational wave. Pulsar timing arrays are obviously important because they will extend the gravitational wave sensitivity to very, very low frequencies. We heard a lot about observations from LIGO and Virgo today that we see in the far right of this diagram in hundreds of hertz. But PTAs can actually probe frequencies at nanohertz, which means that, as we'll discuss, they probe different kind of physical processes. So what kind of sources do we look for? Supermassive black hole binaries are a big part of the sources. We should be able to observe either especially resolved black hole binaries, in which case we will see the deterministic gravitational wave waveforms, which will appear coherently in the different pulsar data. We can also see theoretically, we should expect to see the permanent memory term of supermassive black hole binary mergers, but we can also see different kinds of stochastic gravitational wave backgrounds. Some of them are cosmological, but today we will focus on what we expect from the incoherent superposition of unresolved supermassive black hole binaries. So all these gravitational waves from unresolved supermassive black hole binaries will create these stochastic gravitational wave background, and this is actually expected to be the loudest signal in our frequency sensitivity. So this is the thing that PTAs have been mostly focused over the last decade. So what do we expect to observe? Well, we see here on the first equation that the induced space-time deformation of a gravitational wave background can be described by this dimensionless strain H, which can be expressed as a power law with amplitude A and spectral index alpha. A is typically expressed at frequency 1/year. And this can actually be expressed as a power spectral density in the TOAs of the pulsars with a corresponding spectral index gamma related to alpha. And this index will tell you something about the kind of background you're observing. For gravitational wave background for supermassive black holes, that is at a gamma 13/3. But the spectrum obviously is not enough. We know that there's going to be, theory predicts, to have special correlations between the different, between the induced TOAs of the gravitational wave background on different pulsars. And this is called the overlap reduction function in the context of GER, of general relativity. This is called the Helix and Downs curve that you see here, which basically describes the correlation coefficients in the TOAs of the two pulsars of each pulsar pair with respect to the angular separation between the pulsars. So no gravitational wave background detection can be claimed without measuring this ORF. So with the EPTA, we've been doing background searches for about a decade now, with the first limit in 2011. In 2015, we published the second background with an improvement of a factor of 2, and that came out with the first full data release, the DR1 of 42 millisecond pulsars. But for the background analysis, we only used the 6 best pulsars. Something that happened here is that we started seeing a red noise floor in the data that could suggest the possibility that we're seeing a common red signal. But as the parameter space in the spectrum were very wide, we pursued more data over the next years in order to redo this exercise. And by redoing this exercise with the same 6 pulsars with our data release 2, DR2 noted here, we now have a clear detection of a common red signal, and we are investigating its properties. So just note here that all EPTA results are based primarily on Bayesian statistical methods, but we have also used other kinds of methods, non-Bayesian, to confirm these results. So let's see how this signal looks like. When we search for, in general, for this common red signal in the data, using a single power law as described by the strain of the background, we have on the right the spectral properties for the spectral index gamma and the log amplitude. And on the left, we see our measurement of the overlap reduction function. We see here the 2 lines that show the 95 and 99.5% confidence intervals. And over plotted, we have the helix and Downs curves, and the red points show the angular separations that are 6 pulsars sample. So what we see is that although we are still compatible with the helix and Downs curve, there are other multipliers that can easily fit there. So we actually proceed to a comparison for evidence for the different physically motivated models. Basically, we want to see which of them will actually fit the data better. For that, first I will talk the basics models that we were interested in. So what else could this common red noise be? The most usual suspects for us is a clock error noise. So these are inaccuracies in the terrestrial time standards used. That will cause the same TOA shifts in all pulsars. So this will cause a common signal with a monopolar overlap reduction function. The other possibility is inaccuracies in planetary parameters, whether of mass or orbital elements in the used solar system ephemeris that we use to calculate the solar system barycenter. The effect of that would be an oscillation over time in the calculated SSB position, which will lead to a common signal with a dipolar ORF. And finally, we have the common uncorrelated red noise, which is the result of many pulsars or all our pulsars having individual red noise, but which have similar spectral properties. And the effect with that would be that we will get an apparent common red noise, but with correlation coefficients that are consistent with 0. And this is something we've been worried about for a long time, but it's explicitly shown in a recent work by our PPTA colleagues that has been submitted that this can actually create this apparent common red signal. So we use base factor analysis, which is a way to say which model statistically is more favored by the data. We compare this to our base model, which is pulsar only noise, as I note here with PSRN. And we see clear preferences of any of the models of having on top of the pulsar noise, either a common uncorrelated red noise, a gravitational wave background, or an ephemeris error. The CRN was the most preferred, with the gravitational wave background being on a very close second. And here I want to note that for the solar system ephemeris case, we actually do a lot of investigations because we can actually do a lot of corrections for this, but I don't have time to go into this in detail, but you can ask me questions in the end if you want to. Looking the CURN case more specifically then to do some more investigations, we do the analysis assuming a common uncorrelated red noise with 2 independent codes, which you see here in blue and green with almost perfect agreement. On the left, you see the spectrum calculated on a frequency beam by frequency beam basis of the spectral power. And on the right is the case where we assume a single power law using 30 frequency beams. For the case of the supermassive black hole binary gravitationally wave driven in spirals, the amplitude is around 2.9 10 to the minus 15, which is still in agreement with our previous upper limits and with theoretical predictions. Just to see that what happened since the last effort with DR1, you see here the DR1 results with the pink and the DR2 results with the blue. On the right, you see the two-dimensional stereo distribution for the gamma and log A, and you can see clearly how the result has vastly improved since DR1, and that's obviously thanks to our new data that we have added to the APTA data. And on the left, as you will see the free spectrum, we clearly see that the blue one, it looks like a natural continuation of the pink one after just gathering more data and extending the data time span, and obviously reducing the white noise level of our data set. And to finish off, I want to put this result in some context. So obviously, these similar results have come out by our colleagues in Nanograph and the PPTA. In red here, in this diagram of log A versus gamma, you see our results. We show the 1, 2, and 3 sigma contours. And with blue, you see the Nanograph result, which has already been published, and the PPTA result in green, which is already submitted. Our result is about to be submitted in a couple of weeks. And with the gray area, gray contours, you see the predictions by theoretical predictions that were made based on cosmological simulations by Rosado Sada. And this image is an adaptation from the image from Middleton et al. 2001. So what we see here is a general agreement between the results from the different PTAs. We have to be a little bit careful about the 2-parameter spectrum model that we plot here, because we know that The exact result can depend on the number of fitted frequency bins, and also it can depend on the actual time span of the data, which is different from each data set. So what we're going to say here is that under the assumption, and I highlight the word assumption here, that this common red noise is a stochastic gravitational wave background, we are glad to see that there is still an agreement between theory and observation. And we hope that in the future, in the coming future, we will be able to give some more observational constraints on cosmological models. So I know I'm over the 15 minutes, so I just want to say that our immediate, I'm just finishing. So to just say that our immediate steps, obviously, is to extend our data set to more than 25 pulsars, which were carefully selected based on their noise properties and sky positions, and we are doing more advanced noise models, including looking for possible systematics in the data. And we are preparing our codes for a very demanding analysis that will include more than triple the pulsars and numbers that we're using now. So thank you very much. I will leave you here with my summary, and I'll be glad to take any questions.
Thank you very much. We do have time for some questions. Danai?
Yes, hi. Thank you, Ricardo. Nice talk.
Hi, Danai.
Interesting. I have a question, but I first want to confirm that I understood correctly. So you're saying that this like common red noise that you see could be from individual uncorrelated classical timing noise in the millisecond pulses that you used?
Yes. So basically what happens is that if all these pulses, and we have reasons actually to believe that if they have noise, a sort of stochastic low frequency noise that have similar properties because they may be arising from similar physical processes, this could be confused by the detection code as being a common signal. So I want to highlight that increasing the number of pulsars will help you decorrelate that.
Yes, that for sure, and that brings me to my question. One was, what is the inferred parameters for this red noise that you have for the pulsars? And have you done a comparison with the inferred red noise timing noise parameters for other pulsars? Because there are big studies on how like the spectrum will look like. So you can see if it matches that. And if there was anything special about the particular 6 millisecond pulsars used that could, like some common parameters, common properties that would give them a similar timing noise spectrum.
Right, so let me show you actually. Can you still see my screen?
Yes.
Okay. So, I see what the problem is. I have opened the wrong PTX. So let me close this, and if we have time, maybe I can open the.
I don't think we'll have much time, Vasiliki will get upset, but.
Yeah, anyway, well, I can say without showing that basically these pulsars were basically selected in the past because they had the highest timing precision. So they will actually allow us to probe any kind of signals better, but their sky positions might not be obviously the most favorable to do this. So we need to add more pulsars. So more or less the millisecond pulsars that show red noise actually seem to have very similar properties. So this is why we've been worrying about this. And if I wanted to show you just all this power spectra of the noise of these pulsars, that you would see that they're very, very similar. So either that's because they all have similar noise, or it's because they're all probing, let's say, background or some other common spectrum.
But are the properties of the inferred power spectrum for the noise, the timing noise, consistent with what we get from a much larger sample of pulsars? So, for example, I don't know, the index is usually around 4.
Yes. For millisecond pulsars, yes, actually.
Okay. All right. Thank you. If you can share your slides in Slack, the plots, I would like to continue the discussion. Thanks.
Okay.